Our project was an LED persistence of vision clock, and for those of you who don't know what persistence of vision is, it takes advantage of the fact that your eye can only see at 16 frames a second. So basically if you flash an LED at like 50 frames a second, it'll look like it's constantly on. And so our project used a spinning disc with LEDs behind it, as you can kind of see right here. And as the disc spin really fast, you can light the LEDs up when the slit is at a certain spot, which would show like a second hand or a minute hand or an hour hand. And we used RGB LEDs to differentiate between the hands. And so our requirements were to show the time. Hours green, minutes blue, seconds red. It's pretty simple, but it's hard. And this is our block diagram for the Nexus board. We used a magnetic sensor on the disc to tell where the disc was because it's not a fixed RPM. And we had to interface it with an A to D converter into a GPIO. And basically, this GPIO sent an interrupt, and we had an interrupt controller, several timers, and GPIO to drive the LEDs and the LCDs. And we also had an external motor, which we were going to implement a switch from the Nexus board, but I decided not to. And so it's all external.
Except that you have the feedbacks on the magnetic sensor.
Yeah, the feedback's on the magnetic sensor, so we don't.
We were going to implement a solid-state relay to be able to turn the AC motor on and off, but then we realized it was really just another digital I/O line, and it was going to cost us $7, so we got it.
Keep this one out.
Right now, also our LEDs weren't able to be driven by the Nexus board. It can't source enough current. So we had to use BJT switches with an external power source to drive the LEDs.
So, Sean kind of touched on it already, but the hardware that we used, the basic idea of the two discs, the acrylic that was lit underneath, the piece of Delrin, which is a fairly rigid piece of plastic. We machined out a hole in the top. We actually got a manufacturing engineering student to help us out. And down at the lab, they used their desktop laser to pretty much precision cut all the parts for us. And then in addition to that, they made an adapter to go onto the AC motor shaft so that we could mount that and elevate that disc above. But the Delrin disc limits the light. The BJTs were mounted on an inner circle that was drilled out of the middle of the piece of wood and mounted so that the LED light would shine into the side of the acrylic to be able to get that light to escape perpendicular to that so that we could see it. We planned on trying to frost the surface using the desktop laser that they had to pretty much etch a rough surface over the top of the acrylic, but they weren't able to do that, so we actually just used some sandpaper to sand it down, and that seemed to work fairly well. The Hall effect magnetic sensor that we got ended up being the most difficult thing. We decided to try and build our own electronic analog to digital converter as opposed to using just the PMOD. So we started out trying to use a Schmidt trigger design to do that, and then the necessity for having positive and negative voltage rails kind of shot that in the dark. So we went and ended up using a comparator, just a simple comparator circuit design. But the downside to using that was the comparator was only able to output ground for low and half of VCC. So we had to then try and correct the signal to pull it up to a good VCC value to feed back into the Nexus board, which we ended up doing. We had a CMOS NOR gate that was capable of doing it actually very well. The biggest problem we had with the analog to digital converter trying to design that was the Hall effect sensor was not capable of providing a very large voltage swing between our low input when the magnet was there and when the magnet wasn't. So it actually only had about a 400 millivolt difference. So we had to try and design that comparator network to be fairly sensitive, which it worked in the end, but it took quite a bit of work to get that going.
Our software for the program, it's all interrupt based. Basically the software will receive an interrupt whenever the sensor passes over our Hall sensor. So that basically indicates that one rotation has gone. And we use timers with that, or a counter basically, to count the clock ticks between each rotation. And using that, we can basically kind of like estimate where the position of the slit is in relation to the sensor. And yeah, we use GPIOs to take in the sensor data and GPIOs to output the LED switches, or the LED. Yeah.
So for testing, everything hooked up to the to just the Piedmont headers, and then we needed to use the external power supply so that we had enough voltage, or rather enough current to drive our LEDs. So we actually powered the Nexus board off of the Piedmont header. All the LEDs were controlled. We wanted to try and use components that we already had to minimize costs. So we had a whole bunch of NPN BJTs lying around. So we used that to control each individual LED and just used it as a switch. And then in the Hall sensor to convert that with the comparator and CMOS converter. So that's what we got. The status, I guess, of the design. We actually, I should have said something there. We don't have the clock working. We found that the low-cost motor that we went with has a very difficult time maintaining a constant RPM, and the Hall effect sensor as well still gives us the nice digital input, but it's not always exactly the same. So sometimes it's a little before, sometimes it's a little after. And what we found is that even between one revolution around, the speed was fluctuating enough so that our lines where we were trying to line them up nice kind of moved around and sometimes got off completely. So didn't quite get the clock working due to that, but we could have, I think, with a better motor and probably a better design for our Hall effect sensor for converting that analog signal in. So the back, yeah, we just we mounted everything here onto the back of it.
Oh, wow.
And just made our own little IC board that had all our NPN switches on it. And that's really it. If you guys want to see it, we can, but we may need to turn out the lights. Another issue that we found was that the speed of the motor, which is what we selected was 3,000 RPMs, with the black disc, actually ended up hindering the ability to see the line because it moves fast enough to the point where it actually the black starts to blur in with the color, and it actually limits it a little bit more. We actually were able to fix it a little bit we enlarged the slit that was cut in there, which helped, but we didn't want to go too much bigger. So that's what we got. But we can turn it off, and we can at least see what we do have is a program that does show our best attempt at being able to keep the line steady, even with the fluctuations in them. Or rather, 60, we did a counter that went up for each second around the clock. So that's what we can show. We're over here. Oh, and another fun thing. The motor kicks out a lot of vibration, so we need to get a nice high quality damper to make sure we didn't vibrate the desk too much.
Right on time, huh?
So basically what you can say is you have a proof of concept.
Yeah, definitely.
First.
All right, and the motor takes about 15 seconds to actually reach its max speed. Try and move it around, but actually you really have to be pretty much dead on with it to be able to see the light well, so I have to move it
Let me
around.
turn the monitor off.
Should we turn off the lights?
Yeah.
Okay, yeah. So it's going to keep adding more and more lines until it gets up to 60.
Oh,
Then it'll
I
go back
see.
down to 0.
That's so cool.
Yeah, this thing can't see anything.